Alrighty, and to finish up, we're going to do jitter and shimmer and HNR. So to start off with, jitter and shimmer, these are more intuitive calculations, but when we were talking about jitter, we're talking about the rate of change of the frequency. Shimmer, on the other hand, is rate of change of amplitude. So just like you would if you were evaluating a derivative, all that you do is so this is the calculation for what is called local jitter, sort of the change in frequency. So this t, this is the frequency at point I, right? And we're summing between I equals 1 and I equals n minus 1. Well, what is n? Well, n is the number of samples per window. So let's just say your sampling rate is 10 kilohertz. All that you do is you multiply that by your desired window, and usually the window is about 0.0255 seconds or so. That's what I try to draw here. This is supposed to be a 5. This is like your Gaussian window. This is typically what's used with a little bit of a higher sampling rate, right? Like 44.1 hertz. But for the sake of this example calculation, it leads to an n value of 250 samples per window, right? Because you want a jitter calculation for each window, right? That's how we did it in when we wrote up the code for our project. So all of this is you take the frequency at one point I, and you just subtract that. I apologize. You subtract that by the frequency in the next point, t of I plus 1, and all that you do is you just divide that by the total number of samples minus, you subtract the 1 because you start at the first to eliminate that sort of edge. But very simple. Shimmer, on the other hand, for local shimmer, is the exact same thing, but because we're looking for decibels, all that it is again the same thing. Remember the subtraction of two natural logs. So log 10 minus log 10 of A minus log 10 of B is just, log 10 of A over B, right? So in that vein, rather than doing, T of I and T of I plus 1, you just divide the log base 10, because we're in decibels, of the amplitude at a particular point at point I, and you divide that by A of at I plus 1. And because in essence, we are when we're doing this calculation, we want to square the amplitude when we're making this calculation. So technically, I should have backed up and mentioned this, but technically, it's the amplitude squared that's going in here. So you can factor that out, and log of A squared is just equal to 2 log A. That's the log property that we'd be utilizing there, and so it's 2, and then there's this 10 in front because the definition because decibels utilize the form 10 log base 10 of some 10 log base 10 of some number, some variable. Okay, moving on. So RAP jitter stands for relative average perturbation, I think. Don't quote me on that though. The name, to be honest, doesn't really matter. We call it in our function wrap jitter. But all that you need to know particularly about it is we're just measuring the jitter, so the change in frequency of between like the neighbors of a point. So let's just say you have like some function, you have point I, right? So at that point I, there's going to be the signals at some frequency, right? And by the way, though your sound signal is going to look like all crazy, like with all sorts of sine curves going on, when I say frequency, right, a frequency at a particular time, what I mean is the fundamental frequency that I talked about earlier. So 1 over t peak, right? So what we're doing this is we're actually measuring that change. We're measuring the change in the fundamental frequency at different points, because you can get the fundamental frequency at those different points. Anyways, so now we have the fundamental frequency at point I, right? And all that we're doing is we're adding it up at the frequency at point I, at point I plus 1 and point I minus 1. And we're dividing it by 3 to sort of begin to kind of normalize it. And then we actually normalize it over the average period. That's what this is down there. Before we subtract it from the period at point I. And what the point of this is, we wanted a calculation that gets not that factors in the change in frequency relative to its neighbors on both sides. So not just like this point and this point, but rather, you have a curve and you get this point, and this point, measuring the difference between those three. Anyways. Oh, also, because it's across those three periods with one neighbor, it's n minus 2, because, like, if you have, let's just say, your frequency starts here, and you have your curve, right? If this is a point, and this is a point, and this is a point, you're not going to be able to go, like, obviously, like, you can't start here, right? Because there's no neighbor on this side. There's no neighbor on this side, so that's why the calculation would get confused. And similarly, on the other end, this last point also has no neighbor, hence the minus 2. Similarly, we can compare this to the jitter calculation. So wrap jitter is the same as APQ3 shimmer. As you notice, exactly everything's analogous here. Everything's analogous, except the only difference is that rather than T, we use A meaning amplitude. That's the only difference. There is a log form of this, but I figured I'd just write it this way more simplistically. Now, you've seen this form before, so I figured that I'd just write it this way just to make things more simplistic and easier to understand. Okay, now moving on. PPQ5 jitter. So basically similar to RAP jitter, right? This had a neighbor here and a neighbor here, right? So you have your curve with a point and one neighbor, right? Two neighboring points. Well, for PPQ5, you actually have two neighbors. So now it's a point, a neighbor, a neighbor, a neighbor, a neighbor that you're all factoring in. That's PPQ5. So, I mean, you can start to see the pattern here. It's 3, 5, and then it's going to go up to 11 for a reason I'll explain later. But basically, as you can see, like exact same format, right? So you have your collective increase or decrease or change or whatever's going on. Like you sum all these frequencies up together, you divide them by 5, you see how all of these frequencies all together are different from the frequency at point I. So factoring in the two neighbors, how are the two neighbors different than point I here? And then you normalize it again. You normalize it with the average frequency just to get that value, and this is n minus 4 because there's two neighbors on each end. So similarly, there's one missing, right? But now for this point, it needs 1, 2 neighbors. This point needs 1, 2 neighbors. So because the window is missing those two fringe points at the very end, that's why we use n minus 4 right here. Okay. Now, DDA. So again, this is something that, well, here, let me start with what it is or no, never mind. Okay, well, we'll do this first. So this is for shimmer, DDA shimmer, and what DDA shimmer is it measures the change of the change. So it's like, think of this as the second derivative. So if jitter, I'm combining them. Jitter and shimmer, there we go. If you can think of this as like a first derivative, right? Like you have a change over, like a slope, like a rise over run, a change of y over change in x, that sort of thing. This is like the change of the change, right? So this is just I mean, if we were to start here, this is like the difference between, point I and the point in front of it, right? That difference in amplitude, jitter, or sorry, this is shimmer, remember, so it's difference in amplitude. I tripped myself up there. And we're just again normalizing it with the average amplitude to get the change of the change in shimmer. So this would be the forward change. That's the forward change, and this is the backwards change. And we're sort of taking the difference there, just to get a better picture of sort of that second derivative aspect. And similarly, there is like there is a DDA for jitter as well, and it looks the exact same. Like exact same summation formula. This part is identical. Just replace everywhere you see A, just replace it with T. Just replace it with the period, and you get the exact same value. Okay, now what we're gonna do after? So once we have all of these different variables, right? So it'll look like you have your local, you have APQ3, which is we've seen this. APQ11 and PPQ11 are just they're the exact same as as PPQ5, except now they're with 11 values. So if this is n minus 4, it would become n minus 10, and you'd start at you start farther away. And what we're going to do is, instead of having to deal with all of these components, because individually, while they are important, they aren't that important relative to, say, like fundamental frequency alone, or harmonic to noise ratio, which we'll talk about in a second, alone, or formants particularly alone, right? So we're going to combine them to make a principal component, so altogether they can have something more to offer as a more potent variable. So we're going to use principal component analysis on these variables, and we're going to come up with a jitter principal component, and we're going to come up with a shimmer principal component. And yes, so let's just so the way our code works, right? Let's just say, I don't remember the exact numbers, but let's just say, right, we have you see the Gaussian window, right? Let's just say we have 30 Gaussian windows in a signal, right? So that's like what? 10 Gaussian windows is like 0.2 seconds. So 30 would be like 0.6. So we have a 0.6 second long sound signal, right? So we get 30 different values for jitter and shimmer. We'd probably end up with something along the lines of like 3 different like time intervaled principal components describing the whole signal, which are a lot more useful when combining them. And oh, right, I almost forgot. 3, 5, and 11. The reason why we use the numbers 3, 5, and 11 is because they're the Jacob-Stahl numbers, and they are mathematical numbers that essentially are like, if I were to pick any arbitrary number like PPQ4, PPQ6, whatever, using 1, 3, 5, and 11, mathematically speaking, allows for the most information compression. It's got something to do with, I kind of forgot the details, but it's got something to do with Pascal's triangle, like a lot of the details, I guess. But it's something along the lines of Pascal's triangle. Perhaps next video I can go a little bit more in depth, but let's finish up here. Harmonic to noise ratio, HNR. This is by far one of the more crucial variables. But to get an intuition as to what harmonic to noise ratio is, right? Let's just say you take a recording of a choir singing. You're gonna get a lot of harmonics, right? You're gonna get a lot of that clean sound, right? But let's just say you listen to me like at the beginning of this video, right? Like I was clearing my throat. I kind of sounded very gravelly like this, right? That's an example of a lot of noise in a voice. And typically when someone is tired, right? So when I stood up and I gave like a 7-hour speech, my voice would be tired. I would have a lot of noise in my voice. But if I'm like a pop singer and I'm singing my first song of the day, I'm probably going to start off strong with a lot of strong harmonics. Anyways, that's just sort of to give you an intuitive sense of what's going on. Also I want to mention one more thing. So let's just say you were to look at sound on like a spectrogram, right? So like I'm talking right now, and say I was recording my voice, and there's this spread here, right? Typically the more spread there is, also the more noise there is, right? So on a spectrogram, say like red is of highest intensity. If I was like talking in my normal voice, like there'd be some intense harmonics due to the fact that I'm saying stuff and you guys can hear what I'm saying, and I'm using vowels and whatnot. But there's also definitely going to be like a large share of noise, but sort of the spread, how off the wall the frequencies my vocal cords create is a good indication of that noise. Anyways, how do we calculate it? So what we're going to do is very similar to the fundamental frequency, actually the exact same as fundamental frequency. We're going to do like almost convolution where we're going to dot a function, dot our sound signal x of t with a time average version of itself. And again, just like before, if tau is 0, obviously that's going to be like that's going to make r of tau very, very large because you're dotting a function exactly with itself without any time lag, which is the same as squaring a function, which is high as it's going to get. So what we're going to do is we're going to evaluate r of tau. So at a different tau 1, tau 2, tau 3, different time intervals, right? Like 1 second, 1.5 second, like you go down the list. And within there, right, so when we normalize it like this, you're going to get like some very large decimal values at like some particular points, like, I don't know, say 0.67, right? That's a pretty high decimal value that you can get at one particular tau. Let's just say at T1, you get a value of 0.67. There's going to be some, along with that, there's going to be some values that you're going to get some very low, some time-shifted values that you're going to get some very, very low decimals, like 0.001, right? So that's what we're interested in. We're interested in t, like peak times, and we'll call it t no peak. Not a lot of creativity today. But what we're going to do is we're going to take those peak and non-peak tau values. We're going to time shift those functions. And at the times that we are looking for, right? So let's just say we wanted to, you evaluate HNR at like a particular time. So let's just say we want it at 5 seconds, right? You evaluate that time shifted signal, right? At, the squared amplitude of that time shifted signal. So x of t plus, it would be x of, at 5 seconds, x of 5 plus like whatever tau it is, right? So if we want like to get, say we're trying to find like the harmonic energy, right? So you take x of at 5 seconds, right? So it'd be x 5 seconds of t peak, and then we square that amplitude, and that gives you this guy down here, energy harmonic. And let's just say you wanted noise. So what you're going to do is you're going to do the same thing, except instead of t peak, you use t no peak. Tau no peak at that time, and that'll give you a different value. And all that HNR is it's just the because it's in decibel form, right? So it's 10 times is log base 10 of the harmonic energy divided by the noise energy. Oh, real quick, I also wanted to mention that when you take a dot product of a function like this, what you're also really evaluating is periodicity. So if you have a low t peak, right? So t tau no peak, right? So if r of tau is really low at this particular p or t tau, my goodness. If r of tau is particularly low at a particular value of tau, there we go. That's what I was trying to say. What that implies is that this dot product here is very low. There's very little overlap between the signals, which implies that you're sort of at a spot where there's a lot of randomness going on. And that randomness we can then infer to be noise. There we go. That's what I was trying to say. Anyways, so those are our acoustic, all of our acoustic factors. Fundamental frequency, check. Formants, check. Jitter and shimmer, check. And HNR. So thank you for bearing with me, and definitely let me know if there are any questions. I would love to answer them. And yeah, thank you for your time.